name is Viktor Kirilov, and today I'll be talking about faster builds. So, a little bit about me. Bulgaria, 6 years in the games and VFX industries, last 3 years only open source, and I made DocTest, which is like the fastest in terms of compilation time testing framework for C++. So maybe I know something what I talk about, maybe. And I'm very passionate about not wasting any time, and we're already a little bit behind schedule with this talk. So, C++ is known for a few things like performance, expressiveness, multi-paradigm, but it's also complex. It could be more powerful, there's no standard build system, and it takes a long time to compile. So, has anyone ever seen this meme? Yeah, this is like our favorite thing to do at work. Just Slack where we're waiting. So, this presentation, you can find the slides online at all times on this link, and they'll be available again after that. First, we'll focus on the what and the why, and after that, on the how, like all techniques to actually improve build times. So, in reality, some projects take many, even hours to compile. And it's not just for full builds, but also for minimal builds. Sometimes just a tiny change might result in 10 minutes of linking. And maybe even an hour. They're very, very extreme cases. And that's the fate of all projects which grow big, like it's almost inevitable. And here we can see that the build times for the Opera browser just in less than 4 years grew from 15 minutes to more than 64 minutes. And they even incorporated a precompiled header at some point and slowed the process down a bit, but it wasn't enough. So software just keeps getting bigger and it becomes exponentially slower to compile. So this is something like a unique problem to C++, and people who code in other languages, they just don't get it. How can we wait for hours just to compile a project? But maybe the people from Rust can sympathize with us because they also have big build times. So why would we want to reduce build times? Well, first of all, time is money. Suppose we're receiving that much money per year. And if we waste 1 hour per day of waiting, that's like $10,000 per year per developer. But each developer actually costs a lot more to the companies. Like he brings more value than what he's receiving as a salary. And also companies have a lot of employees. So like investing a few months for a build engineer to fix a build can actually result in huge savings in the long run. And there are also unquantifiable costs like long build times, they discourage refactoring and experimentation, like very much. And also they lead to mental context switches. So you get distracted, you get out of the flow. So the only sensible conclusion is that any time spent reducing build times is worthwhile. So how is C++ built? First, there's the preprocessor, which takes a source file and it smashes all the includes inside of it and expands all the macros, and some code is conditionally compiled, and it results in a translation unit. After that comes the compiler, which takes that translation unit and it compiles it into an object file. And that's comprised of tokenization, parsing, abstract syntax trees, optimizations, code generation. And after that comes the linker, which takes all the object files and also all the libraries and stitches them together into an executable file. And if you really want to learn like a little bit about the history of C++ compilation, you can check out this repository. Again, all the slides will be online at all times. So, why does C++ compilation take so long? C++ is backwards compatible with C, which was a killer feature because it led to high adoption initially for the language. But it also meant that it inherited the textual include approach from C, which was originally just to share a few structures and a few forward declarations, maybe. Even in C, you don't even need actually forward declarations for functions. You can just call functions which aren't declared yet. Also, the language is pretty complex. There are multiple phases of translation, overloads, templates, ADL, and each new standard brings a lot more complexity to the front end of the compilers. Also, we end up building huge zero-cost abstractions, and they usually have to be in headers because in order to be truly zero-cost at runtime in release builds, they have to be inlined, so they have to be visible. And if we're not using Linkdown optimizations, they have to be in the headers. And also for the templates, that's the case as well. Sometimes even the preprocessor can be a bottleneck, and sometimes we just don't use optimally set up build tools and systems. And also sometimes we just mess our project structure, like dependencies are horrible and it's an entangled mess. You touch something, you have to rebuild everything. So let's see the difference between C and C++. If we take a C code base and we just compile it with a C++ compiler, it instantly takes 12% longer on average. But if we take a C++ code base, which is written in C++ 98, and we just turn on the C++ 17 flag for the compiler, same compiler, we just turn on the newer standard, we instantly pay around 30% longer compile times. And new standards will continue this trend. Also, we have meta classes, concepts, and a lot more things which are coming. But also, sometimes const expr might actually help with build times because we can use const expr if, for example, instead of sphinx, and sphinx is maybe one of the slowest operations when we're dealing with templates. Okay. Why do we include suck? Well, they're textual, they're not symbolic, and we cannot cache the results of a header when it's parsed because the next time it's included in a different source file, we can actually have something defined before it, which changes the meaning of the header. And also, overload resolution might play a big part in that. So we just cannot cache the results from headers. And also, because of headers and the fact that the private parts of classes, we still need the definitions for the types which are used by value inside of classes. We still need the definitions for those types. So that leads to a cascading problem of including headers. So you want the banana, you also get the gorilla. Also, we get to compile the same code many times. Like if a header is included in 100 source files, that means that the same source code is compiled 100 times. And also, if we're instantiating the same templates, like vector of integer in 100 source files, the compiler is instantiating the same template 100 times. And also, templates, they just put more code in headers. It's just a requirement. And inline functions, which are like template functions or functions which are just declared explicitly inline. Again, this is not for optimizations, for having them actually inlined, but the inline keyword in C++, it changes the linkage of the symbols. So you can actually have multiple definitions of a function if it's inline. So that's a weak symbol. But then the linker has to remove all the duplicates when it's actually stitching all the object files together, and it has to leave only a single definition of the function in the binary. So that's more work for the linker as well, all the inline functions. So let's see what happens if we just include a standard header and we run the processor. We get like a few, like 10, 20, 30, 50, 60,000 lines of code just by including regex from the standard library. And that's actually more than 1 megabyte of source code. So if we include functional in 100 source files, that's like more than 100 megabytes of source code for the compiler to actually churn through. And sometimes, here are the most expensive headers in terms of time. Somebody else did this benchmark. So more than a second if we include future. And with Clank, it's again more than a second for the same header. Again, if we include that header, or if something else includes it, and we don't really need it, but it's needed as an implementation detail for something else inside of some other header, and we have 100 source files, that's like a few minutes of compilation just because of a single header. And let's look at the boost situation. Well, some of the libraries go almost to 500,000 lines of code after the preprocessor, and that's like almost 10 megabytes of source code. So if we include boost geometry in 100 source files, that's 1 gigabyte of source code. So actually, C++ compilers are doing an amazing job at compiling gigabytes of source code. It's just, maybe takes 1 or 2 hours or many minutes, but it's still amazing. And here the idea is not to bash boost, because actually this is a C++ issue, that it just doesn't give us a proper way of building any other way, zero cost abstractions, and things have to end up in headers. So this is a C++ issue, not a boost one. So also recently there have been a lot of debates about the evolution of C++, mainly by people in the game dev industry, because they cannot afford building in debug. And they have to use release builds because debug builds are just too slow, because all the zero-cost abstractions, if that doesn't get inlined, then it's actually really, really slow. And even their release builds suffer, and they complain about that. So here's one post which bashes a little bit the ranges TS, but it's a debate, you know. I mean, it's hard to say how else things could be. But somebody gave like a good example how something with ranges compiles for 3 seconds, small example, compared to, you know, 70 milliseconds for normal C++. So yeah, zero-cost abstractions aren't zero-cost in debug, and debug builds are too slow, and even release builds are slow in C++. And that's just a problem. There's no clear-cut solution. And also, it's not easy to say that maybe things shouldn't be implemented in libraries, but in the core language, because that has some drawbacks as well. So it's actually, there is no simple solution for C++. Oh, that meme again. Cool. So what can we do about all this? So I should start with disclaimers, because all talks have disclaimers. Well, really good talks don't have disclaimers, so sorry. I haven't personally tested all of the techniques, because there are just too many. I defer a lot to other resources, like I tell you, if you want to read more about the PIMPL idiom, follow those links. And there aren't exact measurements for most of the techniques, but I can tell you like which are the most beneficial ones and easy to implement. So first, the most obvious thing: if you can afford building a debug, you should be doing it, because the compiler doesn't kick off the optimizer, which means faster compilation times. And sometimes the differences can be huge, like a few times faster builds in debug. Also, there are different levels of optimizations, so if true debug is too slow for you, you can have some compromise. And some game studios, for example, they build in debug, but they also enable some inlining as a way to at least a little bit speed up their debug builds. Also, C++ philosophy: we shouldn't pay for what we're not using, so that means unreachable and dead code. We shouldn't be compiling it in the first place. So there's a bunch of tools we can use to actually detect unused functions, or even parts inside of functions which are dead code, which might be considered even a bug. So this is a good idea even for correctness of your source code. And it might even improve runtime, because the less code you have in your final binary, the smaller it is, and the less instruction cache bloating you have. Some other easy to spot things: so you shouldn't have any sources which you're compiling and you don't use at the end. So your builds, if you're building a specific configuration for a specific platform, you should build only the minimum amount of stuff. So maybe a good build system will help, and also a good build engineer, to actually configure things such that only the minimum amount of stuff is actually compiled. And also, we should be compiling each source file just once. So if somebody is lazy and he needs a source file from another project, instead of factoring it out inside of a static library and compiling it once and then reusing it, many people just add it to the other project, and now you end up compiling the same source file twice. And that's just being lazy, and maybe part of the reason is that your build system is just not easy to deal with and move things around. So while we're on the topic of not using unnecessary things, we should remove unnecessary includes, and we should also be striving to include only the minimum amount of stuff that we actually need. So the include everything approach is really bad, because when you touch one header, you have to rebuild everything, because everything includes that everything header. And again, there are a bunch of tools we can use to actually diagnose our projects to see what headers we don't really need. The most famous one is include what you use, which is actually based on Clang, so it can parse C++ code fully, and it can even, I think, suggest like which headers can be removed and substituted with forward declarations. So that's even one step further, not just removing unnecessary includes, but introducing forward declarations. And so now let's talk about forward declarations for functions. Here we see the full function, and which is forward declared, and 3 other functions which are inline. I mean, they're not guaranteed to be inlined by the optimizer, but they're declared inline, so their linkage is weak, and the linker will have to remove all the duplicates in the end when it's stitching all the object files together. So this is the way we can actually have function definitions inside of headers, which end up with multiple definitions when they're included in multiple source files. But that means that the function bodies have to be compiled for all the source files, which include the header, and then the linker has more work. So it's a good idea, in this case, to remove, for example, the bar function and the method from the type outside of the header and put them inside of a source file. And this will improve build times, both in terms of compilation time and linking time. And if you're worried about inlining, you can actually use link time optimizations to get the things inlined in a really performant build, or Unity builds, which we'll talk about later. And we can even factor out the body of the template out of the header, but it has some pitfalls, and we'll cover that later. For types, here we have the following header. We forward declare the structure foo, but we include the header for bar. Why is that? We have a definition of a type, and inside of it, we have a pointer member called foo putter, which is using the foo type as a pointer. So we can go away with a simple forward declaration for foo. But we're also using foo not as a pointer or as a reference, but by value in the forward declaration of f1, the method. And that's actually legal and possible, and many people don't know it, that they can do away with a simple forward declaration even when they're using a type by value in a forward declaration of a function, either as a return type or as a parameter. But where we define that method, we will need a definition of foo. And also where we use that method, we also need a definition of foo. But in the header, here we don't actually need it. But for the bar member, since we're using it by value inside of the memory layout of the class, our new type, that means that the compiler needs the definition of of bar, just to calculate the memory layout, the size of our type we're defining. So this is one of the big problems with header files and C++, because we don't need anything other than the size of bar here in this case. I mean, no, not in this case, but if it was a private member, we wouldn't need anything except for its size. But if the definition of bar requires boost geometry, you know what happens, like 10 megabytes of source code. So here, where we're defining the method, we actually need the definition of foo, so we include the header, because we're actually using objects of type foo. And I actually covered all of these in the previous slides. I talked about them. So on third-party libraries, well, it might be a good idea to try not to drag other headers, like third-party headers, in your own headers, but perhaps wrap them some way or expose just a tiny bit of them. And for example, the STL provides the iOS FWD header, which is comprised of forward declarations for the streams in the STL. And the idea is that if you just want to use std_ostream or something like that as a reference somewhere, like for a forward declaration or something like that, you don't have to include the whole header, which is big, but you can just use this one. And this is actually the only such header in the STL, but many libraries provide alternative headers for their types, which provide only forward declarations. Next up, the PIMPL idiom, which is pointer to implementation or private implementation, also known as a compilation firewall. And the idea is that our type actually holds a pointer to its implementation. And here is how it looks like. We have a widget class, which has a public interface for a constructor, destructor, and a public method. And then inside of the private parts, we forward declare a type called implementation. And then we just define a pointer to the implementation. In this case, a smart pointer, because we don't want to deal with memory management that much. So here we don't need the actual definition of the implementation. And the size of the widget is just the size of a single pointer. And where we're defining the widget, we have the following. First, we define the entire implementation class, which also has, in this case, a full method. And then in the public interface for the widget, in the constructor, we allocate a new implementation. Here we can actually default the destructor, which will actually delete the implementation thanks to unique pointer. And the public method full, we just have to forward the call to the actual full method in the implementation. So, what are the pros of this technique? It breaks the interface and implementation dependency. So we don't have to drag that much headers in our original headers, and also we no longer affect the size of the memory layout of our wrapper types. Also, this technique can be used to preserve the ABI. ABI is the application binary interface. So the idea is that, for example, if Autodesk or some other software which is providing an API, if we have built our plugin and we're using some API which uses the PIMPL idiom, and we've built our binary, our plugin for a specific ABI, and they can actually update their implementation without affecting the binary interface of their application, so our binary can still be linked to their binary. So, but that means that only the implementation can change. We can add more internal methods, more members of our implementation, but the public interface of the wrapper type, it still doesn't have to change. It cannot change if we want to preserve the ABI. So yeah, that's technique which, even if not for compile times, is used for preserving ABI. But there are also some problems, like it requires an allocation, there's also more space overhead because of the pointer, but we can use allocators to mitigate some of the performance problems. There's also an extra indirection of calls, because we have to forward the call from the wrapper type to the actual implementation type. But you can use Linkdown optimizations if we're building one binary to avoid this. And also it's more code to write, and there are a lot more nitty-gritty details about it, which you can read about on this following link, like const propagation, moves, and other topics. We can also use virtual base classes and have some factory functions which return different derived types, different implementations of the base interface through common factory functions. And yeah, this is standard C++, we all know about it, and this way we can hide implementations inside of derived classes which are returned as a pointer. But again, this breaks the interface implementation dependency to some degree. Also, it can help with preserving the ABI, but in this case, if we add a new virtual function to the public interface of the base class, we actually break the ABI. Or even if we change the order of virtual functions, then we again break the ABI. But at least we can add new members to the derived classes, so they can be bigger in size. But since the user is using only pointers to the base classes, he doesn't care. So it can be used in some ways to preserve ABI. But there are, again, problems, like it requires an allocation. Also, my slides are a bit broken. And there's an extra indirection of calls because they're virtual. It's more code to write. Users have to work with pointers now instead of a wrapper type. And Linkdown optimizations, it's a little bit harder for them to devirtualize most of the calls. Next up, we're going to talk about precompiled headers. This is what a precompiled header looks like. It's just a normal C++ header, which is comprised of many headers we actually use commonly in our source code. The idea is that if we're using stud vector in almost all of our source files, we can just precompile it once and then reuse that intermediate representation from the compiler in all of the source files. So it's a good idea to put the following types of headers in a precompiled header. Ones which are widely used across the project, and ones which do not change often, because if a header which is included in the precompiled header changes, we have to recompile the precompiled header, and then we have to recompile the whole project. So we can make some exceptions with some project-specific headers to end up in the precompiled header, but it should be like more stable headers. And we should also audit our precompiled headers if they still make sense. Sometimes we need to add something because a few months have passed and something else is more widely used and it can be factored out inside of the precompiled header. Or maybe something is no longer necessary. And precompiled headers are disregarded by many that they are a hack, but actually this is standard C++. We don't change the semantics of the language in any way. So this technique can actually be employed really, really easy, like in 10 minutes for a project. And the build time can be sometimes even halved for an entire project. If we have 100 source files and we're using boost geometry, it will not only be halved, it will be like even 20% from the original compile time, just if we precompile the heavy header, which is used widely. So many people don't use this, they feel like it's ugly, but it's really not. I mean, if it cuts your build times that much with so little effort, you don't have to change your source code in any way. It's worth it. So how do we use them? Well, most major compilers have flags to set them up, but some build systems support them out of the box. For example, for CMake, there are a few open source modules which deal with precompiled headers, and also fast build, Buck, Meson build systems, they support them out of the box. Next up, Unity builds. Who knows what it is? Cool. So, also known as amalgamated, jumbo, or single compilation units. The idea is that we include a bunch of source files inside of a single source file. But maybe we can, if we have 100 source files, we don't have to include all of them in a single Unity file. We can split it in 10 Unity files with 10 of the original source files in each. So what's the idea here? The main benefit is that, of course, we have much faster compile times. Like, this technique has more potential than even precompiled headers. So if we're using, again, sorry, boost geometry, that header in all of the source files, and we include all the source files in a single Unity source file, and we compile that source file, then we're compiling the heavy header only once. So that's like the biggest reason why Unity builds are much faster. And also there are less compiler invocations. Also, if we instantiate the same templates across many source files, now we're instantiating them inside of a single source file. So we reuse the results from the compiler, and that's much faster. And also, again, this technique is highly underrated, but this time there are some problems to it, and I'll cover them in the later slide. But this technique has the potential to cut your build times like 80%, 90%, even much more. I mean, it very much depends on your code. If you've written very modular code with small source files, like you don't have 10,000 lines of code source files, but they're small, and you use heavy headers and big abstractions, that's where this technique will absolutely shine. And it's very widely used in many game dev studios and also other big projects which are just crumbling beneath the weight of compilation time for C++. I mean, there are even some efforts for Google Chrome, and WebKit is using them, Ubisoft, Unreal. And one other reason for Unity builds to be faster is that there's less work for the linker because you have less object files to stitch together. And one big misconception for Unity builds is that you reduce file I/O from the file system. That's actually almost not a problem with modern file systems and their aggressive caching. So the big reason is that we have less work for the linker, and we compile the same source, the same headers fewer times. So yeah, you can speed up your builds wildly with this technique. And also, one thing which people don't usually think about is that Unity builds are actually free Linkdown optimizations, because what is Linkdown optimizations? You optimize between object files. But here, you don't have many object files. You have probably a single one or just a few. So you have less need to optimize between source files. And you actually have that in a faster build than the normal one. But usually, Linkdown optimized builds are much slower, like sometimes 2, 3, 5, 10 times slower than a normal build. And they also consume a lot of RAM. So you can have faster builds and a more optimized build by employing Linkdown optimization, Unity builds. Also, this is the only reliable way to catch ODR violations. For example, imagine that someone has written a class somewhere in a source file, and then somebody else needs it somewhere else. And instead of factoring it out inside of a header file, he copy-pastes it. And then somebody down the line decides to not see if this class is anywhere else mentioned, because he assumes if it's mentioned elsewhere, it's already in a header file. And he changes the method. Like here, we return something else. So what happens when these two source files are linked in a single binary is that the linker will remove one of the methods, and only the other one will survive, because such methods defined inside of classes are actually implicitly inline, so they're weak symbols. And you might not even get a crash, or you might not notice this bug for a lot of time. But these are very scary bugs, and there is no reliable tooling like sanitizers or flags for compilers. There are some efforts, but Unity builds are the most reliable way to actually catch such errors. Just cram everything in a single source file and try to compile it. And also, if you use Unity builds, you will be using more include guards for your headers. And you won't be copy-pasting code like I've shown above, and yeah. But there are some problems with this technique as well. Some workflows might be a little bit slower, like if you want to rebuild only a single source file, and it's part of the single Unity source file, the huge one, you have to rebuild everything. And also, if you're building all your source files in a single source file, there's nothing to parallelize actually. But both of these problems can actually be solved by configuration and your build system. So again, you don't have to put all the 100 source files in a single Unity source file. You can split them up in 8 source files, so you can run them on 8 cores. And also, if you're going to be iterating on a single source file heavily, your build system should allow to extract that source file out of the Unity source file and compile it normally to a single standalone object file, and then link it to the rest. And so there are solutions to these problems. And the other problems are that some C++ stops compiling. For example, we have the same named symbols in anonymous namespaces in source files, which suddenly end up in a single source file. And there's sometimes overload ambiguities. Using namespaces is a bit problematic sometimes, and the preprocessor can cause a little bit of trouble. But all of these are compilation errors. We catch them, we fix them, everything is fine. The one thing that actually nobody talks about, but is a real problem, is the miscompilation, which happens when actually the project continues to compile successfully, but somewhere, for some reason, the wrong overload is chosen, because something else got introduced which wasn't obvious to the programmer. And this can happen with non-explicit one-argument constructors, for example. And since your code compiled, actually your only line of defense in this case is good tests at runtime. You should validate that the behavior of the program is still as it was. But nobody really mentions it because nobody ever runs into it. Like, it's really rare. So, and you can also use Unity builds only for debug builds. And if you're scared of such problems for your release build, the final build, you can use normal Linkdown optimizations instead of Unity builds for it. So how do we maintain them? Well, for CMake, there are a few online modules. One of them is the compile time reducer. Yeah, it's not very maintained in the past 1 year, but I've been using it and it's pretty good. And you can also see how it's implemented. It's only 6,000 lines of CMake. I mean, yeah. The fast build system supports them out of the box. I'll be mentioning that build system a lot because it supports a lot. And there are some extensions for Visual Studio. No, actually, this is built-in support in the compiler itself recently. And all of these solutions, you can extract specific source files out of the Unity source files, and you can also control how many source files are crammed into Unity files. So the configuration problems I talked about, these solutions solve them. And there are also some more broken slides, as we can see, and other build systems which have some support for Unity builds. Also, recently, some people are trying to get some support inside of the Clang compiler itself for Unity builds, so we don't have to rename symbols which are in anonymous namespaces in different source files, because they clash when we include them in a single source file. So there is some push in the direction of the compiler itself to support Unity builds, and they managed to build parts of Chromium 3 times faster, the parts which they Unity builded with this patch. Inlining, well, it's good for runtime, right? But not always. Sometimes aggressive inlining can actually degrade runtime performance. But here we're talking about build time performance. So we can mark explicitly functions to never be inlined with different attributes for the different compilers. And this leads to a lot of compile time savings, but It might even help with instruction cache bloat. So it might even improve runtime if we don't inline something too aggressively. And let's think about destructors. If we have a function which has like 10 exit points, 10 return statements, that means that there are destructors, sorry, which are called in 10 places. And there are many destructors which get called. And if some of them get inlined, we actually have a bunch of functions which we don't even see originally in our code, which are inlined. And that might actually bloat our instruction cache. So there is an argument against too aggressive inlining for runtime performance, but for compile time performance, it can help a lot with constructs which are very heavily repeated. Like for example, a testing framework, which, how do you write tests? You have a test case with like 10, 50 asserts. An assert is usually a function for testing functions. So if that function gets inlined, you have to compile the same code for that assert function a bunch of times, instead of just compiling a call to it. So that's a place where such inlining can, such preventing of inlining can help a lot. And that's what my testing framework is doing. Like, absolutely nothing gets inlined in the code where users write their tests. And if you're curious more about it, you can watch the cppcon talk about it, how it's implemented with a lot of quirks from C++. Special member functions, we're not going to talk about them. Argument independent code. So here we see we have a template class. It's very trivial, but it will work as an example. So the method and the member, they're actually not dependent on the type itself. But still, when we instantiate this template a bunch of times for a bunch of different types, we have to instantiate the method as well, even though it's literally the same. What we can do is actually factor out the types, the parts of the class which are not dependent on the type in a base class, which is not templated, and then just inherit from it in the template classes. And now we have the easy option to actually move parts of those methods outside of the header, because they're no longer templated, right? So this will improve both compile times and link times if we remove the inline functions from the headers and make them somewhere declared out of line. And yeah, there's less work for the compiler because he doesn't have to compile the same function a bunch of times. And the linker also, we won't have to resolve a bunch of weak symbols and remove the duplicates. And if you're worried about, again, runtime performance, you can rely on Unity builds or Linkdown optimizations to actually have even such tiny functions inlined. But maybe, again, you don't have to go crazy and put every getter and setter inside of a source file. Sometimes it's okay for small functions to be in header files. You should definitely reason about your code, and you shouldn't apply a rule like move everything out of headers, like you shouldn't blindly apply a rule to the full extent. You should reason about your code. Next up, C++11 external templates. Here we have some templates in a header, and somewhere we decide to use them, and we know that we're going to use them only for integer and float, or that in this particular case we're going to use them with those types. And we can say that we want to extern the instantiation of those templates, and that means that somewhere else the template will be instantiated, but not in this translation unit. And then when we use the templates, for example, at the bottom we still use the identity template with a boolean, and we haven't externed it for a boolean, so that's where we instantiate it for a boolean. But above it, where we use it for an integer and a float, we actually don't instantiate the template there for that. But that means that somewhere else we have to explicitly instantiate those templates for those types which were externed in the source file on the right, because otherwise we'll get linker errors. And
you have to use that non-extern implementation to link back to the external one.
Sorry, what was that? Didn't get that.
Sorry, you're saying extern templates are not instantiating that instance on the right, but therefore do you have to use the implementation or the definition in the left file you got?
Yeah, you have to see the definition on the left file where you're explicitly instantiating it. It has to be instantiated in at least one source file in the project, but in the rest of the source files, it can be just externed for the specific types for which it is explicitly instantiated somewhere, at least somewhere.
But the optimizing compiler won't optimize away that definition if it's not used in that file.
I don't think so. I mean, I think even if you don't use identity to float in the left file, in this case, the compiler won't remove it. Maybe the linker might remove the symbol from the entire binary if it's nowhere used, but it doesn't have the right to remove it during compilation. But even if we use external templates, so if we don't instantiate our templates with those types, we still, yes?
Really quick, could you do the instantiation in the header file on the left?
Well, if you do it in a header file, then you have it everywhere. And I'm not sure what happens if you, in the same translation unit, if you both have it instantiated and then externed. I think it will be already instantiated. So there isn't that such an easy solution. Yeah. Yeah. And some STL implementations employ this technique actually for std_string. For example, std_string is underneath a template called basic string. And also, even though we are not instantiating the external templates, we still have to parse the template code. So this technique is nicely coupled with precompiled headers. So we don't have to reparse for all the source files the templates again and again. Because for templates, we have to first parse them as code, and then there's the instantiation. External template deals only with the instantiation part. We can also move function definitions of templates out of header files entirely. And how does that work? Well, where we define them in some source file, the actual full methods, we also have to explicitly instantiate the templates for all the types that will be used throughout the entire project. And then somewhere else, the user can just use the templates for the types, in this case, integer and float. But if he uses it with a Boolean as well, he'll get linker errors, because nowhere in the entire program has the template been instantiated explicitly for a Boolean. And actually, the only place where the templates can be explicitly instantiated is where they're defined. And in this case, they're defined only in the interface.cpp file. So this technique, yeah, you can remove the bodies of the functions out of header files, but the limitation is that you have to know ahead of time all the types that the templates will be used with in your entire project. So you can explicitly instantiate all of those types somewhere. So this isn't like a general solution, especially for libraries, because they don't know what types the users will be using their library types with. But sometimes this technique can help. So templates. There's this thing called the rule of Sheol, and it's like categorization of the cost of operations when we're dealing with templates. And the most cost-free thing, like almost cost-free, is if we reuse a template which has already been instantiated. And the most heavy thing is if we employ Sphinx, which is, if you don't know about it, like there's a bunch of things to read. Yeah. And there was this fascinating talk by Odin Holmes 2 years ago, and maybe 1 year ago as well, who covers a lot of things about template metaprogramming. He actually first talked about the rule of Sheol and this categorization, and you should definitely check it out if you want to be much more into template metaprogramming. Some other notes about templates. Variadic templates, be careful. Recursive templates, be careful, especially if they're not memoized, so if we're not reusing the same instantiations within a single translation unit. When the template arguments are recursive, that also becomes bad, because the type grows and grows and grows quite fast. And now that we have context per if, we can use a lot less Sphinx, and we can use even context per if to avoid tag dispatching, so there are even less overloads to be considered by the compiler. Some tools for templates. MetaShell, interactive template, metaprogramming shell. You can play around with templates, Clang-based. There's also the template tool, which is a profiler for time and memory consumption of template instantiation, and also I think it's a debugger, so you can actually debug your instantiation process of templates. It's used by people who write template metaprogramming libraries. And there's also this IDE which has some support for this. SmartGo talks about templates from cppcon 2 years ago, where Eddie talked about how they reduced at Facebook compile times of thrift-generated code, which originally used a lot of Sphinx, but they ended up using tag dispatching and overload resolution. He also talks about the FTime Reports switch for, I think, GCC and Clang to see where the compiler takes the most time when it's compiling a source file. And also, Olin Holmes, he loves his TMP. So if you want to be better at TMP, watch all of his talks. He talks about different trade-offs when people implemented the different metaprogramming libraries such as Brigand, Quasir, Metal, and others. And some more resources, some templates. Lots of articles to read. Some people claim that they have reduced their build times of their entire projects by 37% by just switching from stud function to a custom rolled one, which is like a lot less templates. And there's a lot of things to do. It's a big space. If you want to diagnose compilation, we have a few tools to help us, but they're a bit crude. So we have FTime Report, the switch for Clang and GCC, but the output from it is not very user-friendly. I mean, it's intended for compiler developers to debug the compiler itself. So you might get like 100 or even 1,000 lines of tables of data about your compilation of a single source file with different compiler passes, and it doesn't mean much to us normal, ordinary people, right? But it exists, and some people have managed to optimize their build times and to diagnose where the problem is in a single source file, which compiles for 7 minutes. I mean, that's crazy. Visual Studio has a bunch of times, BT, time, DT, CG, summary, which has this anomalistic compile times section. So if any function ends up in the anomalistic compile times, that means that you should check it out and try to figure out what's wrong with it. You won't get any much more information, but it means that you should check it out, that function. Also recently, this switch was also discovered. So these are not officially supported switches by the compiler, just like this one. But if you really want to optimize your build times for some pathological case, like a 7-minute build time for a single source file, these switches will help a lot. And some people, after using these switches, like managed to reduce their entire build times by 20% with just a single line of code change. I mean, you can really get some insight using these flags from what the compiler actually is having trouble with if it's something repeated in a lot of places. And yeah, binary bloat. Well, if we're using a lot of, what was it, recursive template arguments and stuff like that, we'll have a lot of big template symbols, and we would like to diagnose our binaries, like which parts are the biggest, what is the problem. So there's Bloaty McBloatface by Google about for Unix binaries. There's also a few tools for Windows binaries, which we can actually see the different parts of the binary. Again, all of these links and the slides, the last slide I'll leave it open so you can see the link to the presentation and check out all of these tools and links later on. And there's some tools from the operating system which you can also use to diagnose the size of the binaries in the different sections. And you also might have to demangle some symbols using a few tools for different operating systems. PGO. Who knows what PGO is? 1, 2, 3 people. Okay. So since we're talk about compile times, we're going to talk about runtime optimizations. The idea is that we optimize our final binary with a profile guided run. So the idea is that first we compile our program with instrumentation, and we have a final binary which is instrumented, and then when we run it through training data, like our typical working set, our binary, it spits out a profile with which functions are most hot, which are most entered, what's the hot path, and after that we can relink the entire binary again using that profile data, And then the optimizer will have better time dealing with what to optimize and what to inline and where. So we end up with a faster binary in the end. The build is a bit more complicated because we have to link twice our binary and we also have to train it with some data. But we can end up with like up to 20% faster binaries. For example, the Firefox browser is shipped with, it is profile guided optimized. So they report something like, I think more than 10% of better runtime because of this. And what we can do is we can build our own compilers with a PGO build. So most compilers have, no, not most, but GCC and Clang, I think, have a target when you're building them, which is for bootstrapping them with PGO. So the compiler boots itself, compiles itself a few times, and one of the steps is generating such a profile. And then it builds itself for the final time using that data, and it's the most optimized version on your platform. And I think you can also build a compiler with a PGO build, not by building itself, but by building your code base. So it can be specifically tailored, the compiler, for building your particular code base. And it's also a good idea to use linked optimizations and a native architecture for your compiler. And if you're a huge organization, this might make sense because you might have 15% faster builds for your code bases just because your compilers are specifically built for your code bases. And there's this talk from 5 years ago from CFPCon where Matt talks about this in a bit more detail about how to do it. Build systems. Well, there are many build systems. And there are also some meta build systems which generate build files for build systems. So first of all, this is not a build system. Again, this is a huge topic, but here we'll just cover it very briefly. Build systems help with dependency tracking. So thanks to them, we can have minimal rebuilds. We touch something and we rebuild only what's affected. They also help with managing scale, like includes, flags, linking, and they also help with refactoring and restructuring of our projects, and also reasoning about the physical structure of the project. And they can help with tool integration. And they're not all created equal. Some are much better in some regards, some are faster, and stuff like that. It's a huge topic. We'll focus only on the speed of compilation and building. So the more old ones, like MS Build and Make, they have some inefficiencies either in the scheduler or when they're scanning the dependencies and what was modified. So there are faster build systems like Ninja, FastBuild, IncrediBuild. They're the fastest in terms especially of parallelization. And we can also have parallel builds with Make with the -j option. We can also even pass it through CMake to the underlying Make build. And for MS Build, we can say that we want a multi-process build for our project with the MP flag. But if we're building projects in parallel in Visual Studio, and each of the projects is building in parallel its own source files with the MP flag, we can end up with a thread oversubscription. Like if we have 8 projects with 8 source files, we can end up with 64 threads. I think that was the case at least a few years ago. Not sure if it's still the same like that. But MS Build is definitely not the best in terms of scheduling of a parallel build. We can use Ninja, I think, instead of MS Build as a Visual Studio backend. There's also this excellent post by Bruce Dawson for making faster parallel builds, especially for Visual Studio, and also diagnosing it. He shows how we can extract ETW, I think, events out of the build process and then plot it in some program and reason about what finished when. You should definitely check out the blog post, it's really good. And also, for parallel builds, we should be careful about long polls. So even if we use Unity builds and we have split, for example, not everything in a single Unity build, in a single Unity file, but a few Unity files, one of them might end up like 3-4 times slower to compile than the rest. And then it might be a good idea to actually split it in different smaller Unity files or just shuffle source files in the Unity source files around, just to make it even again. And as far as parallelization goes, modern link time optimization technology also has some parallelization. Meta build systems. Well, the idea is that there's one canonical description of the project, and then we can generate build files for different build systems. CMake, we love to hate it, but it's the industry standard. It can have some bottlenecks. There's some, for example, this CMake repository, which helps with some CMake checks during, I think, configuration, not generation. And for some projects which do a lot of checks, it might help a lot. We can also build our own CMake with profile guided optimizations, because sometimes CMake might run for 20, 30 seconds or even a minute for some huge projects. It has been shown. So we have a parallel build, but it's not really parallel. There are some holes, and we're not utilizing our system resources to the full extent. And our first line of defense is the task manager from Windows or the other operating systems. I've used it many times to diagnose when there's actually a problem, but you don't get much insight as to what the problem is. You have to figure it out on your own. Again, you should check out that post by Bruce Dawson. It's really great. But what else we can do? We can use Incredibuild, and even though it's a paid solution, we can use it for free on a single machine when we are not doing distributed builds. And I think we get access to the build monitor. And there we can actually see all the build jobs like this plotted and see what took how much and where there are holes in the build. And then we can reason about what should be split in two or what should be reordered. We can also use the Chrome's tracing format and visualize a flame graph of trace events inside of Google Chrome. And there's this Ninja tracing project on GitHub, which I think generates Chrome tracing files out of the Ninja build system. The bug build system also can emit such files out of the box, and there are a few interesting blog posts you can read about it. And also, recently somebody implemented for Clang the FTime trace flag, which is like the FTime report flag for compilation for a single source file. So this is no longer for parallelization of many source files, but if you want to diagnose the build of a single source file, the internals of the compiler, my guess is that in 1 or 2 years we'll have decent tooling with such nice visualizations of what to actually do. So there, I think he's going to make a pull request or something like that. He's going to try to contribute it to LLVM. So in terms of speed, fast build, it says it's fast, should be true. It also supports a bunch of things out of the box like Unity builds, precompiled headers, caching, distributed builds, parallelization, and yeah, I haven't used it yet, but I'm planning on. The other one which is really fast is Ninja, of course. You can use CMake to generate it, or GN, which is specifically, it's a high-level build system, but it can generate only Ninja files. It's called Generate Ninja. So yeah, that's all it does. I think it's used for building Chrome. Also Incredibuild probably is one of the fastest ones, and maybe TUP. If you want to read more about it, you're on your own. And I haven't looked into these sort of modern build systems yet, because it's just too big of a space to explore. Like build systems, you can make a 2 full-hour lecture just on build systems. We're gonna skip this slide. So, how much time we have left? Internal and external linkage. Well, inside of our source files, where we have private details over the source file, we can mark them as static or instead of internal namespaces, so they're not visible from other object files. This is a good idea to do, but the gains will be minuscule. So you don't have to make your code uglier or more obscure just to have like 1% faster builds. Maybe it's not worth it, but it is definitely something. So less work for the linker. And also, if a function is with internal linkage for a source file, and if that function is inlined everywhere, then since it's internal only to that source file, the linker can actually not emit in the final binary the body of the function itself, because it's inlined everywhere. if it's inlined everywhere. So that's possible optimization when we're using internal linkage instead of source files. But yeah, not huge gains from this. Linking, static and dynamic. Well, again, it's a big topic, but prefer dynamic linking. It's much faster because you actually link only the exported interface of the different binaries. And when we're talking about dynamic linking, we should talk about symbol visibility. So on Unix, when we build a shared object, all symbols are visible by default. And that's the opposite of Windows, which maybe for the first time got the default right, where everything is invisible by default, and you have to be explicit about what to be exported. And for Unix, we can use the fVisibility hidden flag. So we make all the symbols hidden by default, and then we have to explicitly say which ones are exported. And this can have very, very big positive effects to link times and also startup times of your binaries and even the size of the binaries. And there are some extreme cases where a program loads 45 times faster just because like a few thousand or tens of thousands of symbols which were being exported are no longer exported. There's also something like that for, I don't know, there are some other flags which you can play with, which is not the big hammer like fVisibility hidden, but fVisibility inlines hidden if you don't want to modify your code. Anyway, you should read up on that if you're curious. But how does explicit symbol annotation look like? Yeah, something like this. Inside of a header, so the top part, all the macros, you can factor it out in a header file only once, somewhere. And then, what do we have here? We have a symbol export and a symbol import defined. And after that, depending on if DLL export is defined or not, my API will either mean export or import. And after that, we annotate our API in our header file with my API. So in this case, the full function and the entire class will be exported. So when we use this header, when we're building the shared object, which actually implements these functions, we define DLL exports. So the shared object will export these symbols. And later, when we're consuming this API and we're linking to the shared object, we just don't define DLL exports. So my API means import. So it's that simple to explicitly annotate your APIs. It's not that much work. And it's good to be explicit about what is part of your interface. And also, linking is faster. A bit on linkers. Well, there are different linkers. For Unix, you can use the gold, which is not the default. And it's not multi-threaded by default, but it can be. There's also LLD from the LLVM project. I think it's even faster than the gold linker. And it's also multi-threaded by default. You can think about the debug information. You can split it from the main binary when you're linking it, and you can have actually better link times when you're doing that. And again, there are many articles which you can read on these topics. Also, you can diagnose, just like include what you use for includes, we have link what you use for CMake to see diagnostic what we're actually consuming, what is actually necessary. So we can remove link dependencies, which we think are dependencies, but they're not really. And also we can build our linkers with PGO, link time optimizations, and native architecture. And a bit on link time optimizations. Well, Clang has this thing called thin LTO, which is a new take on link time optimization, and it's scalable and incremental. And I think it's maybe the most optimal link time optimizer in terms of memory and time consumption. There's also a lot of improvements in GCC, and Visual Studio also has made a lot of improvements in its linker in recent years. They also introduced a new PDB format. Again, the new PDB format is not about link time optimization, but it's just a more optimal format for debug symbols called fastlink, partial PDBs. And currently, Visual Studio also supports link time code generation to be in parallel and also even incremental, which is link time optimizations. And one thing to keep in mind about C++ and the build tools is that compilers They keep making them faster in some cases, but the front end becomes more complex and more complex because of the new standards. But one thing that which only keeps getting faster is linkers, because what they have to do in terms of their job description is basically the same for many years, and they just keep improving upon it. So there's no new complexity in linkers being added. So at least linkers get faster, and the reason that our link times get slower is because our software becomes much more heavier, with a lot more includes and inline symbols to resolve. Caching of compiler artifacts. So what's a compiler cache? The idea is that when we're compiling a source file, we first run the preprocessor, we get a translation unit, and then we get an object file from the compiler. And there are these things called compiler caches, which actually map specific source files, like not specific source files, but exact source file code and exact build flags to object files. So the first time you build a source file, after that you cache for the input the output, which is the object file. And the next time you issue a command of the same source code with the same flags, you actually get instantly an object file for that, instead of issuing the compilation command. So when we're compiling a project for the first time with a compiler cache, the build will actually be like a few % slower, because we'll be doing a little bit more work, like checking with the cache, which is empty, and then we'll have to populate it. But after that, for a full CI build, like on a continuous integration system, when somebody has pushed a change and he changes only one header which affects 10 source files and not the entirety of 1,000 source files, that means that on the CI we can reuse for the rest of the files the object files, so we don't have to compile them, and we'll have to compile only the files which actually changed, which are actually different after the preprocessor. What?
Can you cache parts of the object?
I don't think so. Yeah, sorry. So compiler caches are best for full rebuilds, not for minimal rebuilds, because if you're doing minimal rebuilds and you change something, you obviously change it and you cannot reuse the cache. So compiler caches, they're best for full builds where somebody has pushed a tiny change which affects only a part of the code base. For Unix, there are Ccache, and for Windows, there are a few solutions for Visual Studio. FastBuild, that build system, supports them out of the box. There's also some cloud storage caches and distributed caches. And there's also zapcc, which is not the compiler cache in the terms I just described. Zapcc is actually a fork of Clang, and it works in the following way. It caches mainly template instantiations. So even within a single build which you issue, and there's no cache previously, when it instantiates a template, it caches it. So the next time some other translation unit requests that instantiation of that template, it reuses it. So it doesn't have a cache like normal compiler caches on the hard disk. It's entirely in the RAM. It's like a compilation daemon inside of memory. And even for full builds for WebKit, they claim that WebKit gets built in between 2 and 5 times faster just by switching the compiler to this caching compiler. But since they have a lot of modifications in Clang, like almost 500,000 lines of code, I think, it's open source, but the future of the project is not very known. But if you're not going to be needing C++20 anytime soon, you can rely on zapcc for the next coming years. That's my opinion. What else? So yeah, they work best with full builds, caches, usually. You can integrate Ccache with CMake pretty easily. And there are some other links to check out on the web. Distributed builds. The idea is that we have a network of computers, and not all computers are being used right now. For example, we might use a few cores from a colleague's computer, or we even have a dedicated machine only for building. And when we want to build a huge project with a lot of source files, we can distribute the build of the different source files between the machines. So we ask a scheduler to distribute the work, and a bunch of machines take part of the job. And compiler distributed builds, the tools like distcc is actually just a prefix to the compiler, just like the caches. So we can actually combine caching and distributed builds. We can actually call this TC with Ccache with GCC. So we can have both caching and distribution of builds at the same time. And again, there are some other tools which we can check out. Incredibuild is a paid solution which deals mainly with distributed builds. Many companies which just are tired of long build times just invest $10, $20, $30,000 of hardware and a few licenses, and they partially solve their build problems, partially. And yeah, fast build, again, it supports distributed builds. Hardware, what do we do when we have a problem? We throw money at it. And yeah, feels good, especially if you're not paying. So what can we do? We can get more cores. We also should make sure that we have more RAM to actually not be starved for all the big parallel builds we'll be doing with all the cores. And we can use RAM disks. So SSDs are better than hard disks, but RAM disks are even better. The idea is that you mount a virtual file system inside of your RAM. If you have like a lot of RAM, that's when you can do it. And what you should do is mount your temp directories there and also the output of the compiler, because the linking phase, when you're linking object files which are 50, 100 megabytes big, and if you're using especially Linkdown optimizations, RAM disks do have some effect. But again, this won't help you that much, maybe a few % RAM disks, because nowadays file systems and SSDs are pretty decent. And again, this talk from a few years ago from cppcon talks a lot about the hardware aspect, like much more than my few bullet points I have. They also touch on network issues and other topics. But what if our fundament is bad? What if our architecture is entirely messed up? We should be really thinking about the physical design of our software. Like, it's very often neglected. People don't think about the physical components and isolation. And projects start small, somebody just implements a demo or something, and it quickly grows into the final product without a meaningful architecture in there. And then it's hard to reason about the components and the modularity, and it's also hard to move things around, and also the builds will be slower if you don't have a good physical design. So it's a big topic, I can't cover it here. There are some articles you can check out. John Lakos has actually worked on this part of the physical design for a lot of time. He has a book, he has a few talks about it, and especially the last one is also really good, from CPP Now and I think CPP.com as well. And some companies have gone to extreme lengths in their physical design. And some companies don't allow you to include a header inside of another header. That's it. You have only a depth of 1 in terms of header inclusion. So how do they do it? I think they define all their types only in headers. Sometimes they clump them together, and maybe some for declarations, but they write a lot for declarations themselves. They don't use a lot of TMP, obviously. And they're actually doing pretty good gaming middleware. So the really serious software developers who have decided to go this really radical route to manage dependencies and physical design. And their compile times are just pleasant, really pleasant. They just put it like that way. So you don't have to agree with their approach, but this just highlights the importance of physical design. And when we're on physical design, we need to analyze the dependencies. So we can generate a GraphViz file out of CMake, and then we can visualize it with GraphViz, the tool for visualizing graphs. And some other build systems also support emitting such a GraphViz file. Also, most of the tools for finding unnecessary includes can also be used for reasoning of which includes are not necessary, what includes what. So those tools can be used to reason about dependencies, and a few other tools you can use. And here's an example of a graph for boost variant. I mean, it's not very big. I mean, if you check out boost geometry, it's like, not kidding, maybe 20 times bigger than this. But yeah, when you look at things this way, you get a much better idea of what project depends on what other project. You can think of why that is, and you can try to circumvent some dependencies. But it's really different than just reading source code. But maybe modules will help. Yeah, they'll come from the heavens, and we'll instantly have faster compile times. So a little bit of history. The first proposal was 15 years ago. 15 years ago, yeah. It was dropped from C++11. After that, somebody started working on the first implementation in Clang. Long time ago. After that, the standardization process was picked up again a few years ago, like 5. And it didn't make it into C++17, but it will make it in C++20. I think now it's almost official. And here are the latest papers. Maybe I've missed a few of the latest papers from the latest Kona meeting, but I'll put them there after the presentation. And what's the motivation behind modules? Well, compile times, mostly, maybe, not only. So, also preprocessor includes, they led to the following. We had to leak symbols and implementation details, like a lot. We were having name clashes, and tooling was hard in some regards. We had to use workarounds like include guards. I mean, what is that? Also, the include matter ordered, because if you include sometimes a header before another header, it might have a different meaning, and that's not really clean. Also, with header files, we had to actually repeat ourselves. We had to define somewhere, we had to write forward declarations and type definitions in header files, and then the definitions somewhere else. And we're actually repeating ourselves, and that's more code, and it's not necessary. Here's what modules look like in Visual Studio 2017. We have a module called M1. We define some exported function, and later we import M1 and we use that function. Pretty straightforward, at least so it seems. How we use it? Well, we can call the compiler directly with a bunch of flags, and maybe we get it right and a module is produced and then we can consume it. But how they work? So when we have a module which exports a bunch of things, it produces a binary module interface file, which is comprised only of what is exported. And it is produced when you're compiling a module interface unit, and basically everything that exports symbols, I think, is a module interface unit. I'm not sure. And also modules, they contain the intermediate representation of different constructs and templates, like in a parsed form, just like a precompiled header, for the things which need to be exported. And yeah, mostly for the templates. And unlike precompiled headers, you can have composability with modules, and you can be very explicit about what to be exported and what not to be. And which techniques will be obsolete when modules come? Mostly the PIMPL idiom, but you could still employ the PIMPL idiom if you want ABI stability of your APIs. For declarations, you won't need them because you can actually export right there where you're defining your functions. And precompiled headers will be sort of obsolete, and unity builds will be sort of obsolete. So what's the current state? Well, big companies really want these things to mature and to be created and standardized. Most major compilers support them in some way. They're coming in C++20, but when they're standardized and actually implemented in a uniform way by all compilers, don't expect huge gains, especially in the initially. And also, tooling cloud modules turns out to be surprisingly hard because of the production of those module interface units. No, the binary module interfaces, which are like a separate pass over all your source code to discover what is exported and what comes from where. It's a really messy problem. And currently, only build 2, the build system, supports modules. There are some efforts and some patches for CMake. But again, this is a big problem, and many people are currently arguing all over the internet. And I guess we'll see what happens in the next 1 year. And even when we have it standardized and we have it implemented in the compilers and the tool chains, we'll have to move to newer tool chains. Not everybody can do that. And even after that, we'll have to rewrite our own code using modules, change it. And we'll have to hopefully hope for the best for our third parties, which we use to also migrate to modules. So basically, what I'm getting at is this. We'll be dealing with legacy for a long time. So even in 10 years, I think a lot of code will still be not using modules. Depends, of course, on the companies. And there's a lot more modules, like a lot of talks from cppcon, a lot of articles. And what can we do next after all of these techniques? We can think about runtime compilation of C++. So we don't have to close the program and restart it again just to see our changes. And there are a bunch of techniques which we can use to actually swap code at runtime for C++. We should make our source control checkouts faster. We should have a much faster testing framework for compilation and execution. We can also use ctest for parallel execution of our ctests. And we should speed up our continuous integration. We should have better integration in our IDEs with productivity tools. People don't like to learn new things, but productivity is like such a good investment. Oh, sorry. And also enforcing. If people are left to their own whims, they will do whatever they want to. So there shouldn't be vague rules. Also, there should be enforcement, and because otherwise human nature will prevail, and it will be an entire mess of what guideline was followed and what was not. And so we need code reviews, automation, tooling. Like we need some metrics about the hygiene of our code. We can have Clang-based tools. We can write them on our own. There is also Clang Tidy and a bunch of other Clang-based tooling already out there. We can have pre-commit hooks to not allow code to be submitted to our repositories if it doesn't satisfy some criteria. We can have some other CI checks and a lot of annoying notifications when we break the build, so we don't break it that often. And that's it from me. Thank you very much. I think we have 2, 3, 4 minutes, yeah, for questions. Anyone? Yes?
So I'm particularly interested in compile times for unit testing, so when you're doing test-driven development.
Okay.
It can be super fast, even if the full build is much slower. What kind of advice would you have for that? I mean, should I try and put my unit test into one Unity build, something like that?
Well, first of all, I would advise to use my framework, because actually...
Oh, I should say, actually, that would be great, but I don't have that option at the moment.
Okay. So, yeah, you can Unity build your tests as well. Also, you can use precompiled headers. Those are the 2 easiest things to do. Especially in the case of tests, for Unity builds, there's almost nothing to fear in terms of breaking and compilation errors, because most of the logic and the actual code is elsewhere, and you're just using it in test cases. So you won't have any compilation errors, mostly. And yeah, Unity builds and precompiled headers. And of course, caching, distributed builds, those are the easiest things to employ. Yeah. Any other questions? Well, yes?
I'm interested in the caching builds.
Okay.
Do you know about some common pitfalls for doing caching of builds?
I haven't really used caching. I've just read about it, and I've heard that there are some problems regarding timestamps, for example, on a CI system of the files when they were last modified, or how to save the artifacts, which are the object files. But I can't give you any practical advice on my own. Sorry.
If I'm not going to start a massive new project, big wet dream, but anyway, would it be possible? Is a recommended build environment that shrink wrap build environment that you would know you would go to, which does all this stuff?
Mostly no, because on some of these techniques people don't even agree on. Like some people don't want Unity builds or precompiled headers, or they don't care about compile times that much, so they like put everything in headers. C++ has so many ways of writing it, so
No, I understand, but all the other utilities you have.
yeah, there are many like template projects on GitHub, especially around CMake, which are like a template which you can set up easily with sanitizers, with Valgrind, with code coverage, Doxygen, and a bunch of tools integrated with some tests and some project structure sort of defined. And there's this repository called Awesome CMake. You know the awesome lists? Like there's a big trend on GitHub to have awesome lists, like that's how you name them, and there's a big awesome list with all the awesome lists, and it's like a fight to collect more stars on GitHub. So awesome CMake, it has a lot of such templates inside of it, and by some chance it's mine. Yeah. Any other questions? Cool. Thanks a lot.